So today's event will cover the capabilities of the InfinStore compute platform and MLflow service with a presentation followed by a video demonstration. And there will also be a Q&A session at the end along with more information about the company. So thank you for joining us. And without further ado, I will hand the floor over to InfinStore CTO Jitendra, who will showcase the potential of MLflow thanks to InfinStore's unique multi-cloud compute technology. So on to you, Jitendra.
Thanks, Aditya. Hello, everyone. This is Jitendra Pandey. I'm co-founder and CTO at InfinStore. I have been involved with open source for a while now. I have been part of Apache Software Foundation as a member. I'm a PMC and committer for at least around half a dozen Apache projects that includes Hadoop and Ozone and Hive. And as part of Hadoop group, I have seen the development of Hadoop over many years as part of Yahoo and Hortonworks and Cloudera. So let's first talk about the challenges that we face as an ML platform and the problem that we are really trying to solve here. When we look at how enterprises go about developing an ML model or solve a business case using ML, typically it starts with some bright data scientists coming up with a great idea and doing a good prototype. And we have a big task of taking it to production. And during this production process, it has to go through iterations, hundreds of iterations, and which are expensive, could be expensive depending on the hardware requirements, depending on the data that needs to be processed. And it takes significant amount of time. A single iteration can go up to hours or days. And across all these processes, they need to access to variety of hardware. We see that some hardware may be available in a different cloud or in a different region. For example, if you're using TensorFlow and you need TPU hardware, it is available only in Google Cloud. And some of these problems are not easy to solve with the current technical offerings that we have, like big data clusters are typically homogeneous in nature. They don't offer a variety of hardware that we need for ML. Big data clusters don't work across the clouds. So we see that there is a lack of infrastructure out there to really address these problems. And in this process, we need to scale up and scale down, because if you are debugging something, you want to run on a small data sets, but when you really want to measure the accuracy of your model, you want to run it in really large data sets. And these iterations continue even after you go to production, because new training data arrives, or you get the feedback from the production system, like, okay, we need to tweak our model, or there is a data drift, the statistics of data change, and then you have to train it again. And across all these processes, we need to track the history of your experiments, history of each and every run. You also want to track the intermediate data that is produced in a multi-stage ML pipeline, because that data is really useful for debugging, or maybe for some legal requirements where you want to keep track of the data provenance. So how enterprises really solve this? Today, they are trying to provide an ML platform to the data scientists using with a team of DevOps engineers and data engineers. DevOps engineers manage the cloud resources. They have to operate an MLflow infrastructure or another or a different MLOps infrastructure. They need workflow management systems like Airflow or Uzi, and they have to operate it at scale. For the model deployment, model tracking, again, you need a infrastructure, and data engineers are required to implement some of the SQL queries, or say Spark pipelines, or and to manage the data lifecycle, because the data goes through an ingestion process, and all the when you're using your data for ML training, you need to track which data was used for which experiment. And sometimes it needs the model code to be modified, because if you're using some data frames from, say, pandas data frame, and you want to use a Spark, you have to modify this into a PySpark data frames. So for some of, therefore, data scientists have to work closely with these DevOps teams and data engineers to really come up with a solution that we need to take a model to production. And in spite of all these infrastructure and multiple teams working on it, access to hardware to different clouds is still a challenging problem. There's no infrastructure that offers it right now. Distributed processing for unstructured data is also an unsolved problem, because we see that there are infrastructures for SQL processing, like Hadoop, like clusters do a very good job of SQL processing. But when it comes to, say, audio, video, or image kind of data, we do not have the right infrastructure, and that needs collaborations across multiple teams. So this is the problem that InfinStore is really trying to solve. So we provide a platform which simplifies the lives of data scientists and MLOps engineers, and brings the data lifecycle management, compute management, and MLOps onto a single platform that data scientists can directly work with. It is multi-cloud by design, and it's particularly tuned for distributed processing of images, videos, or any kind of unstructured data. So as part of data lifecycle management, we have two patent pending technologies, InfinSnap and InfinSlice. InfinSnap is a snapshot of your data in cloud object stores. For structured data, we have technologies like Delta Lake that give you time travel feature. But when it comes to unstructured data, where typically the processes run directly on the cloud buckets, uh, you need a similar capability of time travel that InfinSnap offers. InfinSlice is an improvement of InfinSnap, where you can query for the data that was ingested between two given timestamps. This is really useful for use cases like continuous training or incremental training, where new data is arriving on a periodic basis, and you want to run your training or inferencing at a periodic interval on only on the slices of data. In rest of the presentation, I will primarily focus on computation management and MLflow as a service, which is our MLOps offering. So for computation, we have InfinStore Compute Engine that lets you define and process a directed acyclic graph of your notebooks. So essentially, a data scientist works on the notebooks, and we track those notebooks as your ML code or a transform, and then we let you stitch a graph and any arbitrary graph of processing, where output of one notebook can be ingested into the next notebook and the processing continues. So essentially, we encourage a modular development. Like if you have a team of engineers who are working on these different notebooks, they can work independently, and the platform lets you put them together into a pipeline. Also, you can implement your code in the choice of your framework. Like if you want to use TensorFlow or you want to use PyTorch, you don't need to switch to a particular SDK or any particular framework that many other systems require you to do. So this gives you complete flexibility as a data scientist to implement the code in Python in your favorite framework, and we can put all this together into a pipeline. And once this graph is created, then each node of the graph can be scheduled independently in a different machine or a different cloud, depending on what kind of hardware is really needed. Because if a typical ML pipeline consists of some stages of pre-processing, some stages of data cleansing, then a model is created and a model training or inferencing happens. And at different stages of processing, often you need a different hardware. And that capability is available in our platform, which data scientists can directly work with. Now, if your data, you have a really large amount of data and you need to do a distributed execution, we have capability to partition the data and parallelize the execution. This capability is really useful if you want to save on time, or because as I mentioned that these ML iterations can take a lot of time. So if you have parallelized execution, that latency is significantly improved. And if you have use cases like continuous training or a continuous scoring or inferencing, you can schedule a periodic execution, and this is managed through our platforms. You don't need to operate any Airflow or any other workflow management service for that. Now, this compute service works very closely with our multi-cloud MLflow service. So we offer MLflow service in two flavors. One is a standalone MLflow service, which offers you all the MLflow standard features. We support the latest MLflow release in the open source. We have experiment tracking, model registry, model serving. Our service is multi-tenant and highly available at cloud scale. We have tested it up with 1,000 users and running in parallel, and it works perfectly fine. We have added capabilities for Ether authorization policies and access control because in many cases you want to share your models across the teams, or and you also want to share the experiment metadata, some details about the model's provenance. So for that, the right access control policies need to be in place, and we have added that in our service. We also have MLflow tightly integrated with Compute Engine if you're using our Compute Engine, which of course offers all the above capabilities of MLflow. But additionally, you don't have to worry about any MLflow configuration, like you don't have to even specify the tracking server or organize your experiments. If you are using our Compute Engine, we automatically create the experiments and organize the individual runs within it. Uh, Additionally, we track the intermediate data which we index in MLflow itself, and that gives you complete visibility into what your really pipeline was doing. Because if you have multi-stage processing, you want to look at the intermediate data and see if there was a problem, or is the data being transformed in the way you expect. If you are using partitioning and you have a large graph of processing, it's important to track granularly and every node of execution, and that is also available through our MLflow interface. And I will give you a demonstration of these capabilities shortly. So if you are using MLflow and you have defined in our compute engine, and you define a DAG, so we give an experiment ID to your DAG, and every time the DAG is invoked, a parent run is created. And for that parent run, within that parent run, for every node of execution, there is a separate child run ID. And when you go to the MLflow interface, you can look at each and every child, and this organization cleanly lets you look at each and every instance of execution across days or weeks, and you can go back in time and look at, okay, what happened 3 days ago. Similarly, if you are using periodic execution, each schedule is assigned an experiment ID. You can choose the experiment name, but internally we track an ID, and whenever it is invoked, there is a parent run, and all the individual nodes of execution or stages of processing are tracked as separate run ID. And I will show that this gives us really nice capabilities to manage your complicated graph of processing. So let's take an example. This is an example we developed for one of our customers, where they had 3 stages of processing, and the goal was to using some medical images. The goal was to detect if the patient has COVID or not. So first stage of processing is anonymization. These are DICOM images. So idea was to remove some of the personally identifiable data. Stage 2 is to convert the DICOM to Nifty format. And we saw that once you do this conversion, the sizes of the images were reducing significantly. And therefore, the third stage, which is the inferencing stage, we could actually schedule in a different cloud. Because once the sizes are reduced, actually, if you have a cheaper hardware available in a different cloud, the cost of transferring the data is not as much as the saving you get by executing on a less expensive hardware. So in this picture, you can see that the data is coming from the cloud storage, and each stage of processing is interacting with cloud. All the tracking information is sent to the MLflow service, but we also send the intermediate data indices to the MLflow service. So this MLflow service is not only tracking all the metrics and the logs of and the experiment metadata, but it's also tracking the indexes of the data. And that feature we can use very effectively, because in our compute engine, when you are specifying the inputs for processing, you can say that my input is the output of a previous stage. And all you need to say is that use following run ID as an input. And once you provide a run ID as an input, the subsequent stage will directly use read the index from the MLflow service and read the right data for its processing, and will not go to the data source. So by this mechanism, when we are iterating, we can skip the stage 1 because we have run it already once and its output is already available, and we can iterate it over just stage 2 and stage 3. And that saves a significant amount of time as well as compute resources in the cloud, because now we are shortening our iteration cycle. So how does this look in the runtime? That was a 3-node graph, but at runtime, when we have a partitioner, we are running many more nodes. In the actual experiment, the graph translated into 150 nodes. So first stage of processing was split into several nodes. That data was fed into the next stage of processing, and which is again fed into multiple nodes of the last stage of processing. And depending on the computation requirement of each stage, the kind of hardware you're using, each stage has a different amount of parallelization that it needs and that you can control from our platform. Now, suppose something fails at in this process, because we are talking about hundreds of instances of execution, and we know that something can go wrong in distributed processing. There could be a transient network issue or anything. So in that case, again, since we are tracking the intermediate data in MLflow, our engine gives you capability to restart from the failed stage by reusing the intermediate data that was produced by all the nodes that were successful. And that is the reason that we track each and every node of execution separately with a separate run ID, but all put together under a single parent run ID. So this granularity really gives you fast recovery from any failure. So all we need to do is rerun the process. We specify that it is a rerun, and the system will just re-execute the failed node and continue the processing to the following stages. So this is the architecture of our compute engine. It is completely serverless. We maintain the state in the DynamoDB. But apart from that, we don't have any long running service. There is a scheduler which schedules the various nodes of execution depending on whatever is the schedule that is specified or is required. There is a tag controller which basically tracks the dependencies of the nodes, which nodes are successful, which nodes are pending. And once a node succeeds, then it will trigger all the dependent nodes. And the Cloud VM Manager abstracts away all the complexities of various cloud APIs. So the VM Manager works with uh, with Google Cloud, with Azure and AWS, and it's completely transparent to the user. All you need to do is specify the hardware that you really need. Now, there are some details here if you're because since it is a completely distributed system, and also it's very dynamic in nature, because depending on the number of partitions, we have to run different amount of nodes. So we need a distributed locking and coordination so that the shared state is kept consistent. So we have that implementation as well. Our MLflow services infrastructure is again is serverless. It relies on the state in the DynamoDB. Uh, we have some static files which are kept in S3, and that is proxied through Nginx. But in our latest version, we have removed this Nginx proxy as well. So there is no single point of availability here, and it's a highly available and multi-tenant and highly scalable service. So with this, I will now switch to my demo. Uh, So here, as I said, that we tightly integrate with the Jupyter Notebook, and it's available to the data scientists. Our infrastructure, our whole interface is available as a sidebar on the Jupyter Notebook when you install our extension. So I will first show how to capture a notebook as a code to execute in our environment. So I'm just demonstrating a simple hello world execution as an example. So once you try to capture this notebook, you can capture the whole notebook or in just a individual cell. And the key thing here is that we also need to capture the environment of execution, because this Jupyter Lab may be running on your laptop. And so you can specify a Docker environment or a Conda environment. You can copy from an existing another transform, and we provide a wizard where you can choose a base image. You can provide your Linux packages that you need, or any Python package, for example, say NumPy, and you capture it. So, so that's how you basically tell us that this is your code. Uh, and although this is not the only way, we also work with Git. So if all your code is available in Git, uh, you can provide that as well. So once the transform is created, we create a graph of execution. So a graph of execution, again, it could be a multi-node graph, and for each node, you can specify multiple parameters. For example, you specify that I want to process a particular infant snap, and so in here you specify some infant snap or infant slice, or in fact, you can choose not to have an input data, and MLflow artifact if you have a prior run that you want to feed as an input. So you can choose your bucket. Now, all this can be specified here, but this whole thing can be modified at the runtime. So essentially, you are defining a graph with certain parameters, but when it comes to runtime, you can override all these parameters in your data sets, and I will demonstrate that. So you choose your transform, which is executing as part of this node of processing. So yeah, I'm going back to show you that you can actually also specify a Git repository. So in Git repository, you can give a URL. In this URL, you also have your code as well as a Docker file, so you don't have to worry about captured transforms. Now you can specify partitioner. We have some certain inbuilt partitioners, but you can supply your own, and you can state that how much parallelization you need, like how many parallel VMs you want to launch really. You say that, okay, this is the cloud, this is the resource I need to run it on. And similarly, you do the same thing for the second transform. Now, in this case, the input is the previous transform. So you say existing transform and you just click it. So now it will create an edge between the node 1 and node 2. And once again, so you can also specify certain key value parameters, because certain parameters can change while you are actually executing the graph. And so similar kind of inputs here, and the graph will be ready, and then we save the graph. For yeah, if you are using Azure, it will give you the list of instances that Azure offers, and then we just give it a name and save it. And once the graph is saved, it is available for execution in many different ways, and many of these input parameters can be overridden when you are actually executing it. So now graph is saved. So what we do is we actually go and try to run it. So for executing the graph, instead of a hello world, I will use a different graph which is very similar to the graph to the experiment I showed in my slides. So I choose this graph for execution, and once you choose it, now this is the graph in which the first stage is anonymization, and now we change the data set, because I don't want to run it on the full data set. I want to run it on a very tiny subset, so that it completes in the time frame of this presentation. And you can override certain things like, okay, how much parallelization you want to do, or what kind of hardware you want to use right now. And again, we can specify a machine type. So other stages we don't change, and we launch it for execution. So now the request will go to the backend. It is serverless, so a Lambda will be triggered, and that Lambda will basically do the provisioning required for this kind of execution. Now, since you have specified a partitioner, you will see that we will actually modify the graph to do the partitioning. So let's look at the status of this execution. So in here, you can see all prior executions of this graph. We will look at the latest one. And once you click on this, as we can see that the partitioner is running, and the next stage of processing is yet to start. When partitioner is complete, partitioner will have to look into the data and look at the various directories in the data and partition it based on the directories. If you have multiple directories in the input, for each subdirectory, a separate instance will be launched, and we will see that the graph will change once the partitioning completes. So partition is still running. So let's look at what does our MLflow interface show, because all these execution is also being updated on MLflow site. So this is the experiment ID that we created, and we can see that 1 minute ago there was a run launched, the parent run, and has one child run, and that child run is the partitioner. And we can look into it, some of the runtime parameters. It is still being executed, so not much is there right now, but still we can see that there's an artifact directory where we can see some of the things. So once we go back, and now we see that the partitioner is complete, uh, and the next uh, three stages of processing have started. So that is interesting, that why did it start three stages. So we can actually go back to the graph and see that what really happening, or how the graph looks at this point. So we go back to the graph, we look at the run status of the graph, and we see that the graph actually got divided into three threads of execution, one for each partition. And we can see that the first stage is already done, and the second stage has started. And the same thing will reflect on the MLflow UI also. So we have these two interfaces to track your progress. Uh, the graph gives you a visual view because so that you can see the interdependencies and where what is going on. And in this view, you can get into the details of individual runs. So it will take a few minutes to complete. Just bear with me, please. So from here, we can see that uh, for one of the partitions, the third stage has also started executing. So yeah, it is rapidly progressing. It will be done pretty soon. All right. So now in this, now we see that the for two partitions, the third stage has started, but for one of the partitions, only second stage is there. So we see that these partitions are pretty independent from each other. So they are independently being executed, and you are getting a pipelining here because you can go to the next stage of a partition even if one of the partition is not complete, and that is where really we get the performance gain once this kind of pipeline kicks in. Okay, so MLflow tells us that only last two stages of two partitions are remaining. So yeah, we are almost there. So yeah, I'll keep doing back and forth between the two views. Uh, and in here, only one stage is remaining. So that's cool. It's almost there. And once this completes, yeah, we can actually go and look into one of the run IDs and see that what really happened. And the run ID will give us the will tell us the logs or other metadata of the execution. Okay, so everything's done. So let's look at one of the run IDs. So this was the run ID. It shows also the input data, which is indexed into as an MLflow artifact. So you can actually download it from right here. You don't have to go to the bucket. And you can also look at the logs or any other matrix or anything that your process logs. Everything will be available on this interface. So, and the similar execution we can launch from periodically, like if you want to run this particular graph on a regular basis. So you have all the capability to do hourly, daily, or any kind of scheduling executions. You give it a name, and then you provide the name of the graph that you want to run. So, well, you can. Run the graph, or actually you can just pick one individual transformation and run it as well. And you can specify the bucket that you want to process. And and in fact, since it is a periodic execution, you don't have to worry about specifying the timestamps, because when it will pick the timestamp when it is launched. Also, say, for example, if you specify an infant slice, uh, it will, and it's an hourly execution, then it will basically pick the timestamp of the instance it is launched, and it will take that time slice of data in last 1 hour. So that's how it completely takes care of an incremental training deployment. So let's look at the deployment. If you have a model registered, you can deploy it using the platform, and you can choose the hardware that you need. You can choose the type of virtual machine you require for that. And we will also see how we register the model. It is the MLflow registry that we use. You can look at the model. It is completely versioned, and we track the metadata for each and every version. We also track the run that was used to create this model. And once you go to that run, you have all the metadata associated with that run. And as I showed earlier, that these runs are if they're tied to our compute engine, you will also have the intermediate data and source data and all that granularity of metadata associated with the run available. And here you can manage the resources. You can uh, you have a bunch of machines running. You can kill them, or you can pause them. Uh, depending on, how much uh, resource you want to control or offer for your ML experiment. So yeah, that brings me to an end of my presentation. Uh, if you have any questions at this point, I would love to answer.
We had a couple questions during the presentation in our Q&A tab, so I'll just read them out loud so everybody can hear it again. So first question was, does ICE have integration with GitHub or any code repo? And our CEO, Jagain, answered, yes, ICE is integrated with Git. At this point, we can only access publicly available Git repos, one that do not need auth. The next release of our service will include the ability to authenticate to the Git server. And other
Yeah.
question was, what are the different data sources InfinStore can connect to? And so we currently support object stores such as S3, Azure Blob Store, Google Cloud Objects, Minio, etc. And this is for InfinSnap and InfinSlice capabilities. For all other storage types, you can use your native Python library. You can access it as usual because we don't interfere with that.
Yes, yeah, that's the right response. Basically, we have InfinSnap and InfinSlice available on Object Store, but since we support any Python, the generic Python, you can actually connect to any data source.
Anyone else have any more questions?
So yeah, please reach out to us if you have any follow-up questions.
So, oh, sorry. So for anyone interested in the promotional Yeti tumbler, please email me with your work email address and your shipping address. I'll put my email in the chat shortly. And for more information about InfinStore, please visit our website and follow us on LinkedIn and Twitter. I'll put all the links in the chat right now. Okay, so we have a couple more questions. First one, does the distributed processing support for Spark exist? And answer is we are pure Python at this point. And for anyone who would like access to the tool for experimental purposes, feel free to reach out to us.
So yeah, so the question about like distributed processing, yeah, we support pure Python. So if you have PySpark and it is possible to connect toward the external cluster, Spark cluster, but if you have native Python and you want to hook your unstructured data by our partitioning mechanism.
Okay, new question. How about a standalone GUI to MLflow?
Yeah, so we do offer a standalone MLflow service, and it's a fully functional MLflow. All the MLflow APIs are supported, and it's highly scalable and with right access control and authorization policies. We have tested it up with thousands of users concurrently accessing it, so it will work well for your use cases. You will have to just specify your the tracking URL and integrate with your own computation. And yeah, we will be happy to work with you if you want to experiment with our platform. Just drop us a note, and we will set it up for you, and we'll make sure that your use case is successfully onboarded on our platform. We have multiple modes of deployment. We are completely available in Amazon Marketplace as a SaaS model, where the service completely runs in the cloud, and only the data resides and computation resides in your account. We also have an enterprise model where the service runs in your account. You have some additional security requirements, and you don't want any you don't want to work with an external control plane. So in that case, the enterprise model will ensure that even the control plane runs in your own account. So these two flavors cover most of the use cases.
Okay. Yeah, for any other questions, feel free to contact us. Thank you for coming. And yep, we're all done.
Thank you so much. Thanks everyone for joining.